After that kind of exhausting foray into the mathematics of motion, we can finally get back to the physics of motion with Newton's second law. Newton's first law of motion, if you'll remember, stated that unless there is a net force acting on an object, the object will not move or it will continue to move at a constant velocity with no change in the velocity. What Newton's second law of motion answers is what does happen when there is a net force? How does this change the movement of an object? Mass is going to end up being very important to Newton's second law, so I'm going to start this lecture with the book's definitions of mass and weight. So mass is the quantity of matter in an object. It is also the measure of the inertia or sluggishness that an object exhibits in response to any effort made to start it, stop it, or change its state of motion in any way, whereas weight is usually the force upon an object due to gravity. This definition of weight is interesting to me because of the inclusion of the word usually. I would say that it is always the force upon an object due to gravity, but sometimes there is a convention to call the apparent weight of an object in a fluid as the fluid pushes up against it, creating an apparent lesser weight, the actual weight of the object. I don't agree with it. I call it the apparent weight, but if you read the book, I just want you to know what is going on. The more mass something has, the heavier it is, i.e., the more weight it has, but these are not the same thing. Mass is a measurement of how much matter something has. So if you have twice as much volume of a material, you will have twice as much mass, but it has to be the same material. So if you have 2 cubic meters of lead, then that will be twice as much mass as 1 cubic meter of lead. But a cubic meter of feathers will not have as much mass as a cubic meter of lead. So the main difference between mass and weight is that mass remains constant around the universe, while weight is the force due to gravity caused by mass. And then the SI units of mass are in kilograms, while the units of weight are in newtons or pounds for SI and imperial, respectively. We're just going to jump straight into Newton's second law, which is the relationship between acceleration, mass, and force. It can be experimentally found that given the same pushing force, the acceleration of an object is inversely proportional to the mass of an object. A is proportional to 1 over m. Therefore, if you have something with twice as much mass, it will accelerate half as much with the same pushing force. If you have something with 3 times as much mass, it will accelerate 1/3 as much. It is also noticeable that pushing with a greater force will cause a greater acceleration. So we define acceleration to be proportional to F. Combining these and using a definition of force such that the units check out, we find that A is equal to F over m, or acceleration is equal to the net force acting on an object divided by mass, where acceleration and force are both vectors. Doing quick algebra, which we've done a few times, and all you have to do is multiply both sides by m, we can rearrange this equation to the more conventional F equals ma, or Newton's second law. So the units of force are equal to the units of mass times acceleration, which is equal to mass times length per time squared, which in SI is kilograms times mass per second squared, or newtons. A newton is about 1/4 pound. It's a little less than 1/4 pound, and a pound is the imperial unit of force. As we talk about forces, it is useful to talk about frictional forces, which are, if you'll remember, what actually cause objects to slow down and to come to a stop instead of Aristotle's ideal that they just want to be close to the ground. So frictional force is caused by imperfections rubbing against each other between two surfaces. For static friction in a non-accelerating system, frictional force will always oppose the other forces exactly to create zero net force. So if you're pushing at something with 50 newtons of force and it doesn't move, that means that the frictional force acting on it is 50 newtons. If you push it with 70 newtons and it still doesn't move, then the frictional force is going to be 70 newtons. Now, I said that in a non-accelerating system, the forces will create zero net force, but in an accelerating system, frictional force will point in a direction to maintain the same acceleration between the two surfaces. For example, a crate in an accelerating car will have a frictional force in the same direction as acceleration to keep from sliding as the car accelerates. The maximum value of static friction is dependent on the roughness of the surface and the normal force pushing up on the top object. This is usually proportional to weight, but you can engineer systems where it isn't. If the object is moving, then there are sliding frictional forces. So sliding friction always opposes the direction of movement. For given surfaces, static friction is somewhat greater than sliding friction. What this should say is that the maximum value of static friction is somewhat greater than sliding friction. Sliding friction is proportional to the normal force as well, but the maximum value of static friction is proportional to the normal force times a value that is going to make it slightly bigger than the value that you get for sliding friction. So sliding friction depends on normal force, which again, usually weight, and the roughness of the two surfaces, but it does not depend on speed or area of contact. So as you move an object against a sliding friction, it is always going to have the same magnitude of sliding friction no matter what. Let's go back to the idea of free fall. Galileo found that the acceleration of an object in free fall with no other forces acting on it was given by g equals 10 meters per second squared. Because A equals the net force divided by m, the force due to gravity must be given by mg. This is the weight of an object on the surface of the Earth. G is different other places in the universes depending on the mass of the object pulling on our object and the distance from the center of the other object. But interestingly, little g is always independent of the mass of our object. If you go on Mars or the moon or the orbit the sun, you are going to have different values of g and you're going to have different weights, but the acceleration caused by gravity is always going to be independent of what mass you're looking at. Whether you have an elephant or a mouse, they're going to experience the same acceleration. This definition is for free fall, which is when there are no other forces other than gravity acting on an object. However, there are usually other forces if we're talking about an object falling through an atmosphere. These are called frictional drag forces. So in addition to the force of gravity, there is usually a retarding frictional force called drag, written as R. Acceleration is the sum of forces over m, which is equal to the weight minus R over m, which is equal to g minus R over m, which will be less than the acceleration due to gravity in free fall. So R depends on the size, shape, and speed of a falling object. It will get greater as the acceleration speeds it up in a really complicatedly mathematical way. You can take physics 201 if you want to go through that, but for now, we will just say that it will increase along with speed until it reaches a point where R is equal to the weight and acceleration equals 0, at which point it stops accelerating. This speed is called terminal velocity. To finish up, we're going to talk about the velocity of a weighted and unweighted ping pong ball. So basically what this is taking two objects where one is very light and the other is very heavy, and having them have dropped from a high height and seeing if that changes anything. Theoretically, if this is in free fall, it shouldn't. But remember that A equals G minus R over M, where R is a function of velocity. So the two balls have the same drag force for a given velocity because they're the same shape, but the weighted ball has a greater acceleration because it has a greater mass, which means that R over M is smaller. This becomes more apparent the faster the balls go and the more air resistance they encounter. The balls reach terminal velocity when the net force is 0, mg is equal to r, which means that the terminal velocity for the heavier ball will also be greater. This seems to give credence to Aristotle's idea that a lighter object would fall faster than a heavier object. But one thing that he didn't take into account was that there was this terminal velocity that is involved with drag forces. This terminal velocity is also why cats are able to survive falls from high places. Cats will reach terminal velocity after around 5 floors of falling. If it falls for any longer than that, it won't reach any higher velocity, it won't reach any higher speed, and it will be able to stop in the same amount of time as it would otherwise if it were just falling the 5 floors. Backing this up with data, there was a study done with cats which fell from different heights and their survival rates. There were 132 cats, and only about 10 of them died from their injuries. At any floor higher than the 7th floor, cats will tend to splay out instead of landing feet first. And I think that this also increases their drag coefficient. It increases how much air resistance acts on them and would then decrease their terminal velocity. So a cat falling from the 7th floor has the same chance of surviving as a cat that's falling from the Empire State Building.